So when we are talking about high voltage installations, one of the important things that's a merit consideration is that of earthing. And we have to make sure that earthing is properly done so that the system behaves safely and in the manner expected. First, we will deal with a few definitions with respect to earthing. The first definition is that of a system earth. Now, whenever you have a three-phase power system, it has to be earthed. And generally, this earthing is done by connecting at least one neutral. You can have more than one neutral points. You can select more than one neutral points. And you connect the neutral points to a buried earth electrode system. So this is one aspect, that every system has a system earth. And then there is a protective earth, which encompasses the entire earthing system. All non-life conducting parts, metallic parts, are interconnected. They're connected to each other to kind of raise them at the same potential, and then they are earthed. The reason is that we want to protect people from electric shock. So one is the system earth, and then there is the protective earth. We will see how we maintain and interconnect them. Now, under normal conditions, the earth path, whatever is earthed, whichever parts of the system is earthed, should not carry any current. There should not be any residual current in any of the earthed components or in the earth path. But when we have, and that is so, I mean, we do not expect it under normal conditions, that is so. However, if you have very high faults in the system, then these fault conditions, under these fault conditions, there would be a very high current which would flow to earth and would like to find a path back to the source through the earth. And therefore, in these conditions, the earth path can carry very high magnitudes of current. So that's when you have fault currents flowing. Also, if you have lightning faults, in that case also the lightning current will flow to the earth conductors, and either it will be a direct strike, in which case a direct current will tend to flow through the earth's paths, or even if you have high induced voltages, if there is a lightning strike in the vicinity of your system and that results in induced overvoltages in your system, at certain points in your system, then that will cause high currents to flow through the earth path. So these are the situations which need attention. We have to make sure that even under fault conditions, even under lightning strikes or transients, there is no, the earthing is functional and no damage, no high potential rises occur, no damage is caused to the system or personnel. In this respect, we define what is called EPR, or the earth potential rise. Now, the earth is a poor conductor. It has high values of resistance. Ordinarily, the current through earth is very small, and therefore the IR is the potential drop between 2 points which are earthed. I into R does not matter. However, I mean, it's insignificant. But when you are talking about high fault currents or high lightning currents, the current magnitude can be extremely high. It can be in the range of a few 20 kiloamps or even more. And in that situation, if you have a very high current I, which is multiplied by even a small resistance R, the product I into R will be very high. And therefore, if on the earth, in the earth parts, you have 2 points which have a resistance R between them. If R is the resistance between 2 points, even if that value of R is small, a very high magnitude of current will result in a very high IR and a very high potential difference between those 2 points. So therefore, you will have a earth potential rise, these a particular point, if between the earthed system, between the reference earth, let us see there is a point which is definitely earthed, and between them, between that point and another point, you have a very high IR. The second point will rise to a very high potential compared to the reference earth. and this is called earth potential rise. Earth potential rise is defined as the voltage between an earthing system and reference earth. So you may imagine that under normal conditions, this voltage should be 0 or very close to 0 because both are parts of the same earthing system. But under abnormal conditions, even points on the earthing system can rise to very high potentials with respect to ground, with respect to the reference earth. And this potential value is called the earth potential rise, or EPR. The reasons for EPR and the varying values of EPR that you can have depends on many factors. Soil and rock resistivity may vary considerably from region to region. And also, this is a variable, this is a quantity which varies from point to point. So you will not have in any region, geographical region, you will not have a constant value of the resistivity at every point. There is a vertical variation, there is a horizontal variation. So at the point of installation, electrical installation, there are around it a large region which is which will carry the high currents, and the resistance between any 2 points in this region can vary. As a result, you can have high potential rises. The magnitude of the power frequency earth fault currents can range from a few kiloamperes to 20 to 30 kiloamperes. And in the high voltage substation, the earth impedance may lie in the range of 0.05 to more than 1 ohms. So if you look at the resistance, that's a small value. But when you have a very high current flowing, this will cause a very high earth potential rise. This earth potential rise, or EPR, can be as high as several tens of kilovolts. And several tens of kilovolts is dangerous to anything around it. So this kind of EPR is a potential risk of electrocution to people in the vicinity. So if a person stands somewhere and touches a point in the ground which has a high potential difference between another point to ground, that is going to be a problem, and the person may be in grave danger. We will talk about electrocution later. Not only to people and personnel, this may cause also damage to the equipment. And therefore, this is something that needs attention. Now, how do we deal with this situation? In the past, what we tried to do is we tried to reduce the earth resistance value. So we would try to take corrective action whenever the earth resistance value was found to be high. Corrective action was taken in order to bring down the resistive value. Again, we will discuss later how this was done. But there was a specified value, and we had the idea that we needed to bring down the earth resistance below this value. But now we don't care. I mean, our principal aim is not, our principal method of dealing with EPR is not by reducing earth resistance, but rather in trying to control the potential difference. We don't care so much about R. What we care about is the potential difference I into R. There are 2 ways to reduce I into R. One is reduce R, the other is reduce I. No matter how much we reduce R, we don't have that much flexibility. And even with a very small value of R and a very high value of I, you will still have a very large potential difference. So therefore, the first thing to do is try and bring down the current I. And this can be done by designing the earth in a different way so that you don't have very high currents flowing from one point to another. The extent of the rise of potential on the ground surface around a substation can be described in terms of a hot zone. So whenever you have an electrical installation, around that there is a zone in which you expect the potential to rise considerably. And we have to look at this hot zone and try and control the EPR within the hot zone. How do we know how much we should allow the potential to increase? There are standards for that. There are earthing standards which specify step and touch voltage levels which are safe for for personnel, and there are also other standards which tell us how to deal with this situation. So in this respect, first we will talk about system earthing methods. Now, when we have a transmission system, the transmission system takes a very large area. It extends over a very large area, especially when you have an outdoor transmission system. Typically, they have an area of 30,000 meters square, and this requires a main earth grid. The main earth grid is where you have a grid connectivity, a grid which is connected at several points to ground. But apart from the main earth grid, which encompasses the entire outdoor area, what you would also have is, in case of an outdoor transmission line, there are already certain aspects which are part of the earth system. You have the transmission towers which are earthed. You have the earth wire or the ground wire over the transmission line, which has the principal function of protecting the phase conductors from lightning strike, but at the same time, they're also earthed. So the earth wire interconnects the lattice steel towers and is terminated at the substation earth grid. So you now have an extended earth connectivity, which is comprised of the main earth grid at the earth level, and then you have the transmission towers, and then you also have the earth wire over the conductors. At the end of the transmission tower, you also have the tower footing resistance, which can be manipulated. So therefore, the earth impedance of the system at the main substation and at any point along the transmission line is reduced. The earth impedance is therefore reduced because it is an extended system. It's not one single conductor going to ground. It is an extended system. There are grids. There is a earth grid, and then you have the earth wire, you have the transmission tower. When you look at this entire interconnected structure, the total earth impedance from any point on the system to ground is pretty low. As a result, so here what we are trying to do is we are trying to reduce R. Therefore, any rise in earth potential will not happen between two specific points. It will become distributed over a large area. So you will have a potential difference between 2 points, but that will not be between two points which are very close to each other, but the same potential difference will extend over a very large distance. So that means the potential rise per unit length reduces. So this extended earth system is one way to reduce the earth impedance at any point in your system. Then we have what is called the chain impedance. The chain impedance is the impedance of the extended earthing system formed by the transmission line, earth wire, and towers. So you have the earth, the transmission line, you have the tower footing resistance, and you have the grid earth, main earth grid, and then you have the chain impedance, which also takes into account the total impedance of the extended earthing system, which comprises of every earth object or every earth point part of the transmission line. The earthing system of substations in the vicinity will be bonded together. Let's say you have a main substation and in the vicinity you have a substation. In this case, you will always try to bond the earthing system of the main substation with the earthing system of the ground secondary sub-transmission substation. So essentially what we try to always do is try to extend the earthing system, make it as extensive as possible, and try to make sure that it spreads over a very large region. So more components and more greater geographical area. This is true in case of an outdoor transmission system. If you have an indoor substation, in that case, we don't have available such a large area. So the benefit of an extended earth system is somewhat less in case of an indoor substation. If you look at the distribution substation generally do not have these earth wires. They do not have the transmission lines. So therefore, the overhead lines in the distribution substation are not that well earthed as a transmission substation. But distribution systems often consist of a lot of underground cables, and the metallic sheets of the underground cables form an extended earthing system on their own, because each of the metallic sheets are connected to earth points along the circuit. So Every few kilometers, you have an earthing point, and therefore automatically you have a distributed earth system in the cables. So the action of this is similar to the action of the shielding wires on the overhead lines. In the overhead lines, you have the shielding wire, and this shielding wire is connected to the earth at several points. Similarly, in case of the underground cables, the sheath of the underground cable is connected to the earth at several points. So you kind of have the option of limiting the total potential rise between 2 points. Also, the sheath of the cable provides an alternative path for the earth fault current to return to source, and in this way, the path is divided between the earth and the sheath. So there are several paths through which the fault current can return to source, just as in case of the overhead shield wire. The shield wire provides an alternate path for the fault current to return to source. So when you break up the fault current and provide the fault current with several alternate paths, naturally the potential rise along one path reduces. The most common way of earthing any system, as I have already mentioned, is by earthing the neutral. The advantage of earthing the neutral is that if there are any earth faults, and the neutral is earth, it is easier to detect the faults and to clear and locate the fault. Also, during earth faults, earthing the neutral will reduce the over voltage that can happen. The fault over voltage that comes across the system is automatically reduced when you have the neutral grounded. So therefore, apart from earthing, we are also able to address the issue of fault location, fault clearing, and the over voltage due to fault just by earthing the neutral. It is also very convenient to make the connection, especially if you have a star connection. Then you just take the neutral out, use the neutral form by the star point of the supply transformer and connect it to earth. If you do not have a star connected equipment but you have a delta connected equipment, you will need to separate earthing transformer which is star connected, and the neutral of that earthing transformer will be used to earth the system. Earth systems can be of two types. One is solidly earth, the other is impedance earth. Solidly means you do not have any resistance or any impedance between the neutral and the earth point. In impedance earthing, you have an impedance between the neutral points and the earth. The impedance earth systems, of course, can be of three types: the resistance earth, reactance earth, and resonant type. So solid earthing describes the connection of the system neutral point directly to the installation earth. This results in high earth fault levels because you're not limiting the fault current in any way. So the current that is flowing from the neutral to the ground is as high as can be under fault conditions, but it does minimize system over voltages. But we prefer impedance earthing. Impedance earthing, the first kind of impedance earthing is the resistance earthing. So when you connect the transformer neutral point to the earth, you include a resistor between them. So the transformer neutral points and earth are connected through a resistor. This resistor is often a liquid earthing resistor, especially if you're dealing with systems above 11 kV. The liquid earthing resistor is also called an LER. The resistance value was chosen depending upon the kind of fault levels you expect. And your objective is to reduce the fault current as far as possible. So typically, you might be able to reduce you may be able to conduct 1000 amperes at 11 kV through the resistance from neutral to ground. So that is the kind of capability that a resistant earthing might have. Then you have a reactance earthing. As is obvious, instead of placing a resistor between neutral and earth, in this case a reactor is placed between the neutral and earth. Now remember, there might be transient overvoltages across a reactor. So when you have a sudden fault and a sudden current rise, this can result in a high transient overvoltage. When the reactance is high, it might ultimately limit the fault current, but there might be high transient overvoltages when the rate of rise of current is initially is very high, very abrupt. So it is recommended that the earth fault level should not be reduced to below 60% of the three-phase fault level. Otherwise, the transient overvoltages are so high that they are not likely to be very helpful. Therefore, reactance earthing is not considered as an alternative to resistance earthing. They might be used in conjunction to each other. And then we have resonant earthing. In this resonant earthing, we do have a reactor. Similar to the second scenario, you have a reactor which is inserted between the neutral points and earth, and it is so chosen that the reactance of this reactor is equal to the phase to earth capacitance of the system operating under earth fault condition. So under earth fault condition, the phase to earth capacitance of the system is considered, and the reactor has a reactance which is equal to this capacitance, this capacitive reactance. So therefore, what you have is you have a resonant conditions under fault conditions only. This method is known as either resonant earthing. It is also known as Peterson coil earthing under the innovator. There are certain advantages and disadvantages to resonant earthing. During a single phase to earth fault, because of the resonance condition, because you have a high the reactance of the inductor balancing the reactance of the capacitance, arcing is suppressed automatically, and you do not need any extra current interruption. And that means even if you have a fault, you can still continue to operate the network, because whatever capacitive earth fault current is flowing, that will be compensated by the reactive current that is generated. So if it is necessary to continue to operate the system even under fault conditions for some time, that can be done. But the disadvantage is, of course, the transient overvoltages that can happen. Also, there can be steady state voltages on healthy phases during earth. If the earth fault is very high, then it might affect the overvoltage that you are likely to see, the transient as well as the steady state overvoltage that can appear on the healthy phases when one particular phase sees a fault. And therefore, in this kind of scenario, a solidly earth system might be preferable. And the other problem with resonant earthing is, just as you can continue to operate the system under fault conditions, the detection and location of earth fault becomes more difficult.